Howdy, AP Chemistry. We're going to be talking about the wave mechanical model, which was developed by Schrodinger and de Broglie, who worked on the wave mechanical model for the atom. This is after Niels Bohr's development of the atom. And they imagined that the electron was more like a vibrating wave or a standing wave. So where you and I'll explain what the standing wave actually is. It's not like an ocean wave; it's a standing wave. This led them to come up with the wave function, and the way they described it is by using an orbital. The wave function is a function in the x, y, and z coordinate plane. So because we live in a three-dimensional world, and they use the Greek letter psi, which is this letter right here. And you may have heard of the Schrodinger's equation, which he is very famous for. And the Heisenberg's uncertainty principle says there is a fundamental limitation to just how precisely we can know both the position and the momentum of a particle at a given time. We can never know the more you know about how fast a particle is moving or the speed of a particle, the less you know about its position. And it doesn't really make a difference with large objects, but it makes a huge difference with an electron. So we have to go off of a probability standard. So since we're going off the probability standard, we set the marker at 90% of electron probability. That's and that's going to represent the shapes that you're about to see in a second. That's what it means that you are 90% likely to find that electron in that area or in that volume, since we are speaking of in three-dimensional terms. And here's a picture and a graphical representation of it. If we have this would be the 1s orbital right here. This would be the 1s orbital that is just a sphere, S for sphere, and a graphical representation of it, the distance from the nucleus and the probability. So the closer you get to the nucleus, the more probability you have of finding that electron. And one issue to really think about is that this will never actually touch the axis. So you could have a probability of finding that one electron all the way out, as far as you can imagine. But there is some probability, but it's pretty much zero. So now we're going to take it to the next level, or the next sub-level. Electrons are arranged in a series of levels and sub-levels. Now, energy levels are what we have covered before, where they're more like the shells. They're represented by the letter N, and they always have a positive integer. So as they increase, the orbital gets larger, and it also gets farther from the nucleus. And they can also hold an increasing number of electrons. Now, the equation for this is going to be 2n squared. So the maximum number is the maximum number of electrons. The max number of electrons. So if n equals 1, then it can hold 2 electrons. If n equals 2, it can hold 8 electrons. And if n equals 3, then it can hold, that's right, it can hold 18 electrons. So you've heard of 2, 8, 18 before? That's where we get that from. Now, the energy sublevels, there are 4 different types of sublevels: S, P, D, and F. And we'll get to quantum numbers in just a sec. Now, these quantum numbers are not on the AP test, so I'll run through them real quick. The first quantum number is N, and it has a positive integer. And then the next one is the azimuthal quantum number. It shows the sublevel, and where S is 0, P is 1, D is 2, F is 3. Now, these are on the AP test. These are what the p orbitals will look like. These are the p orbitals. And I like to think of them as peanuts orbitals. They are And there are three sets of p orbitals. One electron will be in this one, and one electron will be in this one. One electron, one electron, one electron, one electron. So very nice. Three little peanuts. The next ones are the d orbitals. There are 5 of them, and there are 1, 2, 3, 4, 5. There's 4 daisies and 1 donut. It's a corny way to think about it, but that's a good way to think of how the d orbital looks like. Now the f orbitals, the shape is not tested, but this is what they look like. They're very fancy. These are the f orbitals. Now the magnetic quantum number is going to be m sub l, and it's the orientation of the orbital in space. And the spin is always going to be either plus 1/2 or minus 1/2, the direction of the spin, either up or down. So the spin is something that is tested. It can either spin clockwise or counterclockwise, so north or south. And that actually has something to do with magnetism.